Welcome back to Physics 141 Online. We're moving now into the chapter in the book that deals with the first law of thermodynamics. And it begins with a discussion of a new quantity we haven't talked about before that's called the internal energy. And just to give you a little bit of background, in the mid-1800s, the modern theory of heat replaced what was called the older caloric theory of heat. That earlier theory thought of heat as a substance, and the name they gave it was caloric. And they thought that when objects were placed into contact, that caloric from one object could transfer to the other object, much in the way that fluid could flow from one container to another. And this really wasn't quite right from our modern perspective, because it thought of heat or caloric as something that belonged to a substance. And we now understand today that heat is an exchange of energy that's based on the motions of the atoms and molecules inside a substance. And when you put two objects together, what happens is the molecules and atoms collide with each other, and slowly over a period of time, as the systems approach equilibrium, energy gets transferred. And so the person who more than anyone else was responsible for this modern theory of heat as a form of energy was James Joule. And of course, the unit for energy is named after him. Joule did some actually very clever experiments using a paddle wheel turning inside a container of water to show that the heating up of the water that was caused by the turning of the paddle wheel was very closely related to how much energy had been used to make the paddle wheel turn. And so over a period of time, people began to realize that heat was just another form of mechanical energy, and that mechanical energy and heat could be exchanged. Mechanical energy could be turned into heat. This was really the beginning in the mid-19th century of the modern theory of thermodynamics. So what is this internal energy before we talk about the first law of thermodynamics? Well, just to review, mechanical energy, the symbol E that we've used in the book and in our class, is the sum of the kinetic and potential energies, but these are associated with the position and the motion of the center of mass of an object. So if I throw a brick through the air and we look at the motion of the center of mass, its speed determines, and its mass determine the kinetic energy. The height of the center of mass above the ground, above the earth, determines the potential energy. But even if that brick were just sitting on a tabletop and not moving at all, there would still be energy associated with the kinetic and potential energies of the atoms and the molecules and the nuclei inside the brick. See? And it's that energy that we call the internal energy. So usually in the kinds of problems we've been doing, let's say collision problems, we haven't been worried about those kinds of things, because if two pucks collide on an air table, certainly the molecules that make up the puck, those are moving as well, but as a result of that collision, none of that energy really changes very much. We've certainly been ignoring that, and we've just been focusing on mechanical energy. Well, now that we want to understand thermal energy better and heat, we have to talk about the motions of the atoms and molecules inside the object. Now, an ideal gas is a great model for us to study, because in an ideal gas, the molecules are far apart enough, because we think of it as a dilute gas, so that the molecules don't interact strongly with each other at all. So there's no potential energy of interaction. Likewise, we can ignore the kinetic and potential energies of the nuclei of the gas molecules, because those are the protons and neutrons inside the atoms. And those energies don't change unless something really extreme like a nuclear reaction is taking place. And we're not going to study those in this course. So we already know from our kinetic theory of gases, for this kind of an ideal gas, if it's monatomic, if it's something like helium, where the molecule is simply a helium atom, we know that this internal energy will just be due to the translational kinetic energy of the gas molecules. And the kinetic theory of gases told us that for a gas composed of n molecules, this kinetic energy of translation is 3/2 n times Boltzmann's constant times the temperature. And if we want to rewrite it using the number of moles of the sample rather than this huge number of molecules, this becomes 3/2 nRT. So for an ideal gas that's monatomic, we already know the expression for the internal energy that it has. Notice, of course, that it depends on the temperature and nothing else. So the temperature of the system determines how fast those molecules are moving, and that's what makes up the internal energy. But for other kinds of molecules, it gets a little bit more complicated. For a diatomic molecule like oxygen, or for a polyatomic ideal gas molecule like methane, for example, those kinds of molecules have not only translational energy, in other words, they don't only just move through a container, but the atoms both vibrate, and then the molecules themselves can rotate around some sort of rotation axis. And so that means they have other forms of energy besides just translational kinetic energy. They have vibrational and rotational energies as well. So again, we're going to neglect the nuclear energies. And the way our textbook does this, it says, well, in general, we can write down the internal energy of a gas in terms of its specific heat measured at constant volume. So don't worry about where this comes from. This is just the most general way of writing it down. And then we'll see where the specific formulas come from in just a moment. So apparently then, if this is true in general, we already know that for an monatomic ideal gas, the correct expression is 3/2 nRT. So apparently the CV, C sub V, must be 3/2 R for a monatomic ideal gas. If we plug that into this expression, that would give us the 3/2 nRT that we already know is true. But we can also see, and this is in the textbook as well, that this specific heat can be written down quite generally for a specific kind of gas molecule using a constant gamma. That's what this curvy Greek letter is here. That's a lowercase gamma. And so it can be shown, and we're not going to do it, but it can be shown that this specific heat at constant volume is equal to the gas constant divided by gamma minus 1. And for a monatomic system, this gamma is 5/3. So if I just plug in 5/3 into that expression, R over 5/3 minus 1 is R over 2/3, which is 3/2 R, right? So this specific heat for a monatomic gas is 3/2 R, which then plugged into the expression for U gives us the internal energy for that kind of gas. And what we really use this to calculate is not so much the internal energy of the gas at a particular temperature, but rather the change in the internal energy as the temperature changes. And so here in the red box is the formula that you will be using as you do homework problems in this part of the course. I'll show you also what the result is for a diatomic system, because there are some homework problems dealing with diatomic gases, and they're also very common in nature. The oxygen and nitrogen in the room are diatomic gases. So this gamma factor is 7/5. So 7/5 minus 1 gives us 2/5, which is going to make that C sub V 5/2 R. So that means that for a diatomic gas, the only real change is in this fraction out in front of the nRT. So that delta U, the change in the internal energy for a diatomic system, is 5/2 nR times the change in the temperature. So these two equations here are the important ones to remember and be able to use when we're looking at processes involving specific gases. All right, with that background, with that very simple understanding of internal energy, we now can write down the first law of thermodynamics. And here's where it comes from. The internal energy of a system, whether it's a gas or not, but we're thinking about gases here specifically, can only change through one of two processes. And of course the one that we already know about is the transfer of thermal energy into or out of the system. So Q, we call that the heat, but it really means thermal energy. If Q is positive, that means the system is absorbing thermal energy. If Q is negative, it means the system is releasing it. And those kinds of processes will raise or lower the internal energy of the system. But there's something else that can happen. If we've got especially a gas inside a cylinder, and if that gas can either be compressed or that gas can expand, then work is being done. If there's a compression, work is being done on the gas, which would tend to raise its internal energy. If the gas is expanding, it's pushing on the piston, and then work is being done by the gas, And so then its internal energy would go down as a result of that. And so the first law of thermodynamics is really just a bookkeeping device to express this form of the conservation of energy for thermal energy processes. So delta U, the change in the internal energy, is equal to the Q plus the W. Now the signs are always important when using equations like this, and let's just make sure that this makes sense. Q, we know, is positive if heat is absorbed and negative if heat is released. And if you had a positive Q in this expression, that would mean heat's being absorbed, and it makes sense that that would tend to raise the internal energy. And I just said a minute ago, if work is being done on the system, which is a compression process, then we would be putting energy into it. We'd be raising its internal energy. And so again, that's why the plus sign is here. The sign convention for work, so that it is consistent with this equation, is indeed positive work means system is done on the system. That's a compression process. Negative work means work is being done by the system as it expands, as it goes to a higher volume. So this formula we'll be using quite extensively in this part of the course. Now, in order to be able to use that formula, we have to be able to calculate the work done on a system through various kinds of processes. In general, this can be quite a complicated calculation to do, but for certain special cases, we're going to find out that calculating the work as the pressure and volume of a system, a gas system, changes is pretty easy. We will be introducing the use, in this part of the course, of a pressure-volume diagram to describe the state of the gas system. So what we're going to do first, as our prototype example, I've already mentioned that you can imagine a cylinder full of gas with some kind of movable piston enclosing the gas. So the motion of the piston to the left or to the right, shown here in the gray, is going to cause the pressure and the volume to potentially change. So what we're going to do is come up with an expression for the work done on the gas by the piston if there's a force F applied to the piston, and assuming that the cross-sectional area of the piston is A. So we're going to consider a very, very small compression of the system by an amount dx. So a constant force F pushes on the piston, it moves a small distance dx, and we want to know what's the work done on the system in that process. And it's pretty easy to do because we remember from our discussion of work that work is force times distance when the force is constant. Okay, so here the force times that distance dx is equal to the differential amount of work that's being done, dw. Well, force, we remember that the definition of pressure is force per unit area, right? So if P is F divided by A, then M can be written as P times A. All right, so in a case where this is this force being applied causes the piston to move slowly, then we can assume that the pressure inside the gas, everywhere inside the piston, stays the same. And so it's going to be done slowly, and there's a fancy word for this describing this kind of process that we'll define in just a minute. Anyway, now that we've got an expression for this differential amount of work as P times A times dx, we now can write it down in terms of the change in volume of the gas inside the cylinder, and A times dx, right, the cross-sectional area times this small distance, would represent the volume between the piston and the dotted line. But we have to put a minus sign in there because dV, the change in the volume in this process, is actually negative. We said that before, that when the change in volume is negative, when the volume goes down, it's a compression process, and that makes the work be positive. So if we want the work to be positive, and if dV is negative, we need to put a minus sign out in front. So what we've now determined is that if we can take the pressure times the change in volume, we get the work that's done. Okay, and now here, the special kind of process that we're talking about, and we will be assuming this in most of the calculations that we do, is a quasi-static process. And what that just means is that it's done slowly enough so that the pressure throughout the gas stays the same. If, by contrast, if I hit the piston with a hammer so that a compression was done very suddenly, the pressure right near the piston head would be greater than it would be somewhere else inside the cylinder. But if this force is acting to move the piston slowly, then equilibrium is maintained throughout the gas, and the pressure is the same everywhere inside the container. So for this kind of a quasi-static process, the work done on the system is the integral of this quantity P dV as the system goes from some initial to some final volume. So it's minus the integral P dV from V1 to V2. And you may not have done a lot of integral calculus, but we've used integrals in a limited way earlier in the course, and we're going to use them here to be able to calculate the work. The nice way of understanding this is we remember that integrals are really areas under some kind of curve. And so I'll show on the next slide that the work done is actually minus the area under the curve on a pressure volume diagram. So this is now the starting point for us to be able to calculate work for special kinds of thermodynamic processes. And here they are. Calculating PV work for special processes. In general, on a pressure volume diagram, when a gas is compressed or when a gas expands, it goes from one point, from a certain pressure and volume, to another point. And that can be very complicated. But often there are ways of arranging for processes to be certain special kinds, where in one case an isobaric process, iso means the same, baric refers to the pressure, it means that the process happens at a constant pressure. So the system goes from V1 to V2, the arrow indicates the direction of the process, and here the pressure stays fixed. So remembering that the work done for that kind of process is the area underneath the pressure volume curve, it's just the area of this rectangle here, right? So I can start with the definition. Work is minus the integral P dV from V1 to V2, and if that pressure is constant, as it is in this sort of process, it comes outside the integral because it's not changing. And so when that happens, we're left with this really simple expression, the integral of dV, which we understand that's just the summing up of all the volume changes going from V1 to V2, and in fact we just get V2 minus V1. So it's negative the pressure times V2 minus V1. And the reason that the answer turns out to be negative is because what I've drawn on the sketch is an expansion process. So work is being done by the gas. It's expanding. And our convention for the use of W is that that sort of a process would have to have a negative value for the work. All right. Then the second kind of process that's special, the pressure and the volume are both changing in this sort of process, but it's happening at a constant temperature. In other words, it's happening along what's called an isotherm. And an isotherm is a line on a PV diagram that connects pressure and volume values that all belong to one specific temperature. So how do we analyze the work done by this kind of a process? Well, we have the same expression to start with, minus the integral P dV from V1 to V2, but now what we're going to do is plug in for P the expression from the ideal gas law, right? And so P is nRT over V. Now why did I do this? Well, because it has the volume dependence, which we know has to be inside this integral. All right, so if we have a dV here, then it's nice to have V itself in this expression. And even more importantly, what we can now do, since this process is isothermal, that means temperature stays the same, we can pull outside the integral the temperature. And of course the N and the R are constants for a particular sample as well, so they come outside as well. So what we get, we pull the nRT outside, and we end up with minus nRT times the integral from V1 to V2 of dV over V, and I won't work this out in detail, but this is one of those special kinds of integrals that you may already have learned in your calculus class, and it results in a natural logarithm function. And so when the smoke clears and you do this integral, you get minus nRT times the log of the ratio V2 to V1. And since in this process V2 is greater than V1, it's going to be the log of something greater than 1, which is positive. But again, the minus sign guarantees that the work done will be negative, because again, this is an expansion process. And finally, and this one's the trivial one, a process that occurs at a constant volume is sometimes called an isovolumetric process. I think some books also refer to it as an isochoric process. But if that's the case, let's say that a gas goes from a lower to a higher pressure, but it does so at a constant volume, well, the work done for that is 0. And I'll just ask you to think about that, starting from the definition of work on a pressure-volume diagram. Can you see why the answer is 0 for an isovolumetric process? It shouldn't be too difficult to convince yourself that that's the case. So, in summary, what we've done is define internal energy for a gas. We've written down and explained a little bit how the first law of thermodynamics works. It's a conservation of energy statement for heat and work done on a gas. And then we've defined work and how we calculate it on a PV diagram, and have done that simple calculation for 3 special kinds of processes. So this should be very helpful in understanding the background that goes into homework problems that we'll do in this part of the course, and I will do some examples in class.